All right, so today we're going to completely shift gears. So, like I said last time, we've completely covered the theory of spectroscopy from the wave function all the way up to the simulated spectrum. Okay, and that's the particle in a box spectroscopy. That's what that whole book was written about. But the math, again, is quite involved even for a one-dimensional system. And so today we're going to shift gears and we're going to start talking about symmetry and how that helps us jump to the conclusion of the selection rules. So all of those selection rules that we determined last time, that for the particle in a box, the transitions that were allowed were the odd ones, jumping by 1 or 3 or 5 levels. Those were the selection rules. Those were the non-zero probabilities of a transition when light comes in and interacts with the system. We can get there really quickly with just like 4 lines of simple math if we use symmetry. So that's what we're going to shift gears today and start talking about symmetry. And so one of the things that we have in symmetry is a reflection plane. And now every time you see reflection in a pool of water, you're going to think of a reflection plane because I'm turning you into chemists, okay, whether you want to or not. So you can see in a reflection plane, if I have a point anywhere, let's pick let's find one that's easy to see. Let's pick this little branch up here, okay? If I look straight through the reflection plane, I see the same thing, okay? And so in molecules, we have reflection planes. So if my head is an oxygen and my hands are the hydrogens, these two hydrogens can reflect into each other. So there's a reflection plane right here. And so that's one of the things that you have to start seeing now. And it's an acquired skill, but some people struggle with it, and so this is completely different. Sometimes people are awesome in the calculus, and that's just the way they think. They want to do the calculus, and they get to this part and they struggle. Other people absolutely can't stand the calculus. They see sine and cosine and they go like this, but then they see the reflection planes and they're like, I love this. So I don't know who you are, but you know who you are. That doesn't mean you can skip one and just study the other. About half the exam is the vocabulary of spectroscopy that we've covered so far. The other half is the symmetry stuff. But here's a molecule. Does it have a reflection plane? Does it have an inversion center? And so really work hard this week to get ready for the exam because there's a lot of little details and you're going to work on it on your lab section this week, whether you're on Monday or Wednesday or Thursday, and that'll help you prepare for the exam. So let's start with symmetry elements. Now we did all of this math in the book and looked at it in class, and it took about 4 pages of calculus and algebra to get to this point right here, the selection rules. So we saw what this intensity equation was, this integral, and we had to do this huge integral and know something about cosines and when it was even or when it was odd. We got different results and so on. And so the non-zero pieces, this right here, happened when delta n was odd. So plus or minus 3, 5, 7, etc. Were the transitions that were allowed. And they were allowed by the overlap of those wave functions when they interacted with light. Well, we can do that in symmetry. Symmetry provides a fast path to this point right here, which is fantastic. Okay. So let's learn a few things. So it looks like math, but it's really vocabulary. Okay. So what we're learning now is about even and odd functions. So if we go to the left on this function, so this wave function up here, think of f of x, and we're going to minus x. We're going to a certain spot, minus x. So in this case, we're going to minus 70 or whatever, and we're evaluating the function, and we see its positive value. Okay. If we go the same distance in the other direction and evaluate it, we see it's the same value, same sign and same magnitude. That's the definition of a positive or an even function. So by definition, this is an even function. Now, can you see the mirror plane right here? If I were to draw a mirror plane that's supposed to be kind of coming out of the board, you know, if I reflect that function right here in a mirror, the left and the right side look identical. Can you see that? I see lots of nods, which makes my heart warm. Okay, that's a good thing. Okay. Now let's go to the other one. This n equals 2. I go to the left a certain distance and evaluate the function, and then I go to the right a certain distance, and it's the equal magnitude but opposite sign. And so that's the definition of an odd function. Okay. What we're looking at is these numbers in front. So when this number in front, so f of minus x is equal to f of x, that's an even function. And f of minus x is just minus 1 times the f of x. That's an odd function. And those plus ones and minus ones in front are what we call characters. So that's a new term. This term characters, because we're going to get into symmetry, collections of symmetry operations, and we're going to have what's called a character table. It's going to be filled with plus ones and minus ones. And you may have the question at that point, where did all these plus ones and minus ones come from? And this is a good example of that. We go left on the function, we evaluate it, we go right on the function. If it's the equal magnitude but opposite sign, then it's an odd function, and it's a minus 1 character. Okay. So let's look and try to figure out our selection rules. So first of all, any other questions about this? There's two types of functions, even and odd. Okay. And then I guess the third type would be functions that don't have symmetry. But these functions have symmetry. They're even or odd. Okay. Now what can we do with that information? This is beautiful. Look at this. The integral of an even function is non-zero. It doesn't tell me what it is, but it tells me it's non-zero. Okay. But even more useful than that is the integral of an odd function is equal to 0. So I can go through and I can see if the integral of something, if that's something in the middle of the integral between the integral sign and dx, if that function is odd, I know the integral equals 0. I don't have to go to sine of integer multiples of pi, or I don't have to evaluate cosines of odd delta n's, and even I don't have to do any of that. If I can determine if that function in the middle between the integral and dx is odd, I know the whole thing's 0. And we just skip past 4 pages of math. I like that. And there's multiplication rules. Now, we've used the terms even and odd since we could first count numbers, right? When we started thinking about what was divisible by 2, that is not what we're talking about here. We're really talking about that symmetry around the axis, whether it's even or odd. And so when we do multiplication tables like this, we really need to be thinking in terms of plus ones and minus ones. Think of those characters. So if I have plus 1 times plus 1, what's the result? Plus 1, yeah. And then if I have plus 1 times a minus 1, what is the result? Minus 1. So even and even gives you even times odd gives you an odd function. So that's the multiplication rule. So here we have an even function times an even function, and we get an even function. Or if we have we could just get rid of the f and g and h and talk about terms of even. And then if we have even times odd, that's equal to odd. What if we have 2 odd functions? What do you think? Sure enough, if minus 1 times a minus 1 gives a plus 1. So just think in terms of plus and minus 1s being the even and odd. And then also you can do multiple ones. So I have 3 minus 1s. Okay, minus 1 times minus 1 is even, but then times another minus 1 now becomes a minus 1 and it's odd. So we can go on and on and on with all of these functions. So we just keep multiplying these functions, and if we know their symmetry, we don't actually have to do the trig or the calculus. I got a sine function times a cosine function times something else times x. And if I know the symmetries of those, I don't have to do the algebra. I don't have to do the calculus. I can just look at the symmetries of those functions and tell you if that integral is 0 or non-zero. So let's practice. Let's do the transition dipole moment integral for this piece right here. So we're going from wave function 2 to wave function 1. So let's say we're going down like this. And I have a question mark here, like, is this allowed? Okay. So we can look at this equation and we can say, well, these are the symmetries of those functions. The wave function 2 is odd. We determined that just a minute ago. The x-axis is odd. Well, just think about the x-axis. Over here is a positive 100 and over here is a minus 100. So it's odd. And then wave function 1. You can see the reflection plane here. You know, if I go to the right and evaluate it, and if I go to the left and evaluate it, it's the same magnitude, but the same sign. So that's even. Now, let's just work ourselves right to left. That's typically the way this is done. So odd times odd is even. And so we just carry that down. And then this even comes down. And now we have an even times an even. Okay, and that gives us even. And so remember these brackets. The brackets are an integral. So we're taking the integral of an even function. So I know that that's going to be non-zero. So this is what we say about this transition. We do this little symmetry math, and you guys are going to do these a whole bunch of times through the whole semester. Okay, so this is a procedure that you'll do to show me this transition is allowed. So we say that this intensity is non-zero because it is allowed by symmetry. So the symmetry of the functions allow this transition to take place. Yes. Correct. Well, we're not really addressing it in any way except that when we get to that non-zero result, we'll just square it. So if it's negative, it becomes positive, so we're good. Yes. Yes. Um, we typically put the initial state on the right side. Yeah, that's just a tradition because X represents light. And so it's coming in and it's impacting that wave function. So the operators come in from the left. Think about the second derivative operator, right? It's on the left side of the integral that it's operating on. So that's why we put the initial state at the right, and then we operate on that initial state, and then we come in with a final state to see if it interacts with the result of that operator operating on the initial state. So we sort of read them right to left. Just like in math, if you're taking a function and you do the derivative, you put the derivative on the left and you operate to the right side. Yeah, you didn't even know you were doing that, but that's what you've been doing all this time. As you come in and take the derivative of a function, you operate it on it from the left and operate it. And then if you have something else coming in, you come in from the left and multiply. So, yes. Yes. So if we take, let's just, forget everything that's on the screen. And so we have X and Y right here. And if we plot f of x equals x. So we could just make that function f of x equals x and we plot it like this. Then, as a slope of 1. And so if we come over here a certain distance and we go up and evaluate it, and then we go left a certain distance and we evaluate it, it's equal magnitude but opposite sign. Yeah. So x is always odd. Now when we get to Raman's selection rules, we'll use x squared. And so let's determine the symmetry of x squared. So in this case, it's hard to draw straight lines, I'm sorry. So f of x equals x squared. And so that's going to be a parabola, right? So x squared. So we're going to start here. If I can't draw a straight line, I wonder if I can draw a parabola. Okay. It helps to stick your tongue out. Okay. So here's x squared. Best I can do. And so if we go to the right and evaluate it a certain distance, and then we go the same distance to the left and evaluate it, they're equal magnitude, equal magnitude, same sign. So it's even. So x squared is even, and x is odd. And we could have also gotten the x squared being even by taking two x's times each other. So we have an odd times an odd to give an even. Yeah. Great. So this whole piece right here is very important because we'll hit this a whole bunch of times. And then it gets a little more complicated when we go to 3D systems. We're not going to do triple integrals, okay? But we can do crazy complicated symmetry calculations, and it's all very short and sweet. This is not something you're going to see much in the PChem textbooks, which is a mystery to me because PChemists all around the world teach symmetry, but they kind of treat it like a trivia game. It's like, what's the point group of water? What's the point group of ethane? and you learn the point groups, but then you never use them in spectroscopy. And so that was a strength in my graduate program. And so then I've always just taught the usefulness of symmetry to determine whether these transitions are allowed. So y'all are getting a little extra boost in the symmetry area. So that'll pay dividends someday, I hope. Okay, so let's determine these things. These are the values we got from our analytical results and our numerical results. But let's see if we can at least get the zero and non-zero nature of these transitions. So here we're starting in state 1, and we have x, and then we're ending in state 4. So we're going from n equals 1 to n equals 4. And first of all, we need to put the even and odd pieces on here. Is it okay if I use E and O instead of spelling out the whole thing? So we're just going to use E for even and O for odd. So down here at the bottom, n equals 1. Well, let's do 4 since it's on the left here. So up here at 4, you can kind of see, look at right here where this box is blocking it. Look at the behavior right here at 0. Do you think, what is this, even or odd? Yeah, see if I go a little bit to the right and evaluate it, it's positive. If I go the same distance to the left and evaluate it, it's negative. Same magnitude, opposite sign. So 4 is odd. We just draw these vertical lines just to separate them. It's just to show, these are multiplied by each other, but we're just drawing vertical lines just to separate the functions. So x we just determined was odd, and then we draw another vertical line, and then 1 down here at the bottom. You can see its behavior around 0. You can see that it's even. Now you know why I want that wave function centered on 0, don't you? You know, I put that extra phase shift in there so that all my wave functions are centered on 0, and it's easy to see whether they're even or odd. Okay. So let's now evaluate these a piece at a time. So we start with the right. Odd times even is odd, right? -1 times +1. And then we bring this down. It looks like zeros, but these are O's. Okay. And then odd times odd is even. And then we have the integral over all space of an even function. And so that's not equal to 0. And sure enough, it's not. It's equal to 8.3 after we square it. Yeah, we could put the squares on there if you want. Yeah. So that's cool. That took a lot of math, and we did it in 3 lines. So that's neat. I like symmetry for that reason. Okay, let's do this one. 3. 3 is even. You see here at its behavior around 0. It's just a mirror image of itself. So that's going to be even here, and odd there, and 1 is even. So odd times even is odd. And we bring even down here. And then even times odd is odd. And so we have the integral over all space of an odd function, and that's equal to 0, which we knew, but now we've shown it by symmetry. Yes? Yes, in all our problems, yes. And so this one is allowed by symmetry. And we would say this transition is forbidden. So the symmetry forbids light to be absorbed by those wave functions. Okay. That's cool. Okay, we're going to now shift from one dimension to multiple dimensions. And to do that, we need more than just this sort of reflection in the x-axis, because we have 3 axes and there's lots of things that can happen. We could have rotations, we could have reflections, we could have things called inversion and so on, and these are symmetry elements. So we're going to start expanding our vocabulary of symmetry and our understanding of molecules now into 3 dimensions. So this is the first time we're going into 3 dimensions in this course. So now start thinking about real objects. This is the spectra that we have of real world evidence that symmetry is an important thing. So water and CO2 both have 3 atoms. Okay? And yet look at their infrared spectra. They're very different. This is the rotations on top of the vibrations in the infrared spectrum. And water is crazy, crazy, crazy. Look at that. There seems to be no pattern. These are the rotations of water on top of the vibration. And there's tons of transitions, okay? But look how orderly CO2 is. You've got these two major peaks, and then each one of those is just a bunch of little rotation lines, all equally spaced. It looks beautiful. It kind of looks like the particle in a box spectrum that we had, where you had equal spaced lines. Okay, and over here we have equally spaced lines with a peak in the middle, and it's the same on both sides. We have equally spaced lines here, just beautiful rotational structure. Okay, and this peak in the middle. And why? Well, the answer is because, well, you tell me why. What's the difference between CO2 and water? Double bonds, that's interesting. This is in the infrared, though. Good answer. This is in the infrared. So this is talking about vibrations and rotations. So the electron cloud is what's holding the molecule together, but it's not involved in this spectrum. But that's a good answer. Yes, and so we're going to have some terms for that about their point group. So that's the answer. In this case, we're talking about rotational structure. So CO2 is straight and water is bent. So CO2 is a linear molecule. So it's oxygen, carbon, oxygen. And it can rotate this way, okay? And it can rotate this way, but notice that the moment of inertia is the same, whether it rotates this way or this way, because the distance of the oxygens from the center of rotation is the same, no matter how it rotates. And in fact, you might think it could rotate this way, but there's no mass off of that axis, and so that rotation just disappears, doesn't exist, okay? So there's only two rotations for CO2, and they're the same. So the symmetry of the molecule gives you these perfectly spaced transitions, and it's all beautiful. Water, you've got this, you can rotate water this way, okay? Does y'all see these are the hydrogens, okay? And so their distance from the axis of rotation is this distance right here. So that's one moment of inertia. You could rotate it this way, okay? And so then the distance is this distance from the axis of rotation, which is different than this one. So that's a different rotational structure. And then this way, okay? And so then their distance is from the center of mass, another different distance of how they spin. And now the oxygen is involved in that spin. Three different rotational moments of inertia. So we have three different spectra on top of each other for the water because it's bent, okay? So right here, this is a spectrum, just atmosphere. You know, we got CO2, we've got water, and we can see the need for symmetry, or we can see the effects of symmetry in these two molecules. Here's another example. CO2, the vibrational transitions themselves. One of them is only present in the Raman, and the other one is present in the infrared. And this is the bending mode. It's present in both, but this one, the asymmetric stretch like this, so this is now the carbon and the two oxygens. This is the asymmetric stretch, that's in the infrared. And in the Raman, this is the symmetric stretch. So this is an even motion, and it interacts with the even x squared operator in Raman, and its symmetry allows it to be present in the Raman spectrum, but not in the infrared. So we see symmetry in both of these examples. So for one-dimensional systems, it's really easy. We've got one function, you can plot it, you can see it. Particle in a ring is pretty easy too. That's just a particle spinning around an axis. These are capital, all caps easy. The H-atom radial wave function, so the distance of the electron from the nucleus. Again, that's a one-dimensional system. It's lowercase easy. Okay, we could do that one pretty easily. But then we get into complicated systems. All molecules are complicated because we're dealing with three-dimensional setups. And so molecular orbital theory helps us understand diatomics. And then symmetry helps us understand symmetric molecules. And then if you've got an asymmetric molecule like DNA or whatever, local symmetry helps us with that. So symmetry can even help us in really large asymmetric molecules. So this is the point. we like to know the selection rules of spectroscopy. So is this transition allowed? That's sort of our governing question. Given, say you have a complicated molecular orbital and you've got one down here, say it's a pi and a pi star, think back to organic, okay? Is this allowed with in the visible spectrum? Is this, the energy difference between these? It looks like this compound should be colored because this difference would give us a peak in, say, the red region of the spectrum. So that would give us a blue compound, okay? But is the pi to pi star transition allowed? Okay. That's the question we're asking. And so that would be a selection rule question. Is light allowed to make this transition? Well, to determine that, we need to know the character table and the direct product tables. So the direct products would be this even times odd times even terminology of the pi and the pi star orbitals. So that's the direct product tables. To get those, we need the character tables, okay? And the character tables are what I call the Rosetta Stone of spectroscopy. Do y'all know about the Rosetta Stone? You may have heard that. It's like a software for teaching languages. It was really an amazing thing. We knew ancient Greek, but we did not know the Egyptian hieroglyphics. So you see in Egypt all of these fantastic things. We think maybe that's some kind of writing or whatever. The Rosetta Stone had the same speech or the same text written in 3 different languages. And so this was the key to learning Egyptian hieroglyphics. And spectroscopy to you at this point may be like Egyptian hieroglyphics. You got all these crazy peaks, but we know Vesper shapes. Do we know Vesper shapes? Trigonal bipyramidal, yeah, trigonal planar and all of that. So if we know that, then this symmetry gets us to understanding the selection rules. So the character tables have everything in it. The symmetries of the vibrational motions, like this asymmetric stretch in water, okay? It also has the symmetries of the molecular orbitals, like the pi and the pi star transitions. It also can determine, which we won't do in this class, but you guys have studied NMR to some degree, it also would help us identify identical nuclei in the NMR. And then we get the character table by determining the point group. So the point group is a designation for that molecule. It has a particular symmetry. And so we will identify that point group, and that will tell us what character table to use, which will tell us what direct products to use, which will allow us to answer our question of is this peak or transition allowed. And then how do we get the point group? We need to know the geometry of the molecule. So that's this week's lab. You're going to draw a bunch of molecules. You've got a molecule set too. You'll build a few, and then you can practice your drawing of molecules. Because if you draw it correctly, then you identify the point group, and then you can identify the character table. So all of this rests upon your ability to do Lewis dot structures and Vesper shapes. So hopefully that's the tip of the ramp. You're down here at the tip of the ramp. But if you can do Lewis dot structures and Vesper shapes, which you'll practice this week in lab, then you'll be able to get the point group. And that's the main part of the test, is identifying the point groups and the coordinate system. So basically the symmetry piece of next week's exam is what you're doing in lab this week. So stay the whole time, make sure you understand it. Your TA's paid to be there, so don't leave early. Like, this is your time to really get good so that you can do well on the exam. Okay, so we start with this Lewis dot structure, and we use the electron domains to determine the 3D structure. Now, if you're weak in this is an OpenStax book. Some of you folks were short-sighted as freshmen, and you sold back your chemistry book. I don't want to know who it was. But there's an online freshman chemistry book, and it's decent, okay? So you can go here, it's OpenStax, OpenStax, and you just type in, you can do chemistry OpenStax, and you'll get a link to it. And go in there, you can look at the review the Lewis dot structures and Vesper shapes if you're a little weak on that. Okay, so use that 3D structure to determine the point group for the molecule. We'll practice that today and on Wednesday. And so here's an example. The one on the left I call the freshman Lewis dot structure, because everything looks like it's in the plane. Okay, you know what I'm saying? And there you go. We got 4 domains and so on. Now you can determine, yes, that's got 4 domains and it's sp3, but an sp3 atom has a tetrahedral electronic structure. And so you should have the little dashes here, like this. Notice these two hydrogens are really close together. This is a very important point in your ability to draw molecules. Okay, when we take these two hydrogens right here, and we say that this angle is not 90 degrees. 90 degrees, it's really 109.5. Then we've got to get that hydrogen away from this hydrogen. And it moves up, okay, this direction. And this one, this angle is 180, right, in this picture. And that's not correct. It should come back to 109.5. So it moves in this direction. And in our perspective, they pop in and out of the plane of the paper. Okay, so they're in front of each other. So draw them as if they're almost in front of each other so that you can see the threefold symmetry. If you were to look down at this end of the molecule, you should see the carbon atom, and you should see like 120 degrees between these hydrogens. It should look like threefold symmetry so that you see this rotational symmetry here. Do y'all see that? The three hydrogens are going to be equally spaced from each other, 1/3 of a turn. That's important because we're going to be talking about rotational symmetry, and this has threefold symmetry, meaning if I rotate this 3 times, this hydrogen goes, where's this baby? Okay. Let's just mark this hydrogen. If I rotate it once, it ends up here. I rotate it a second time, it ends up here. I rotate it a third time, it gets back to where it was. So that's threefold symmetry. How many times can I rotate it for it to come back? Threefold, okay? Very important. And so these are sp3 atoms. Now here's a trigonal planar carbon atom right here in the middle of acetone, and that would be an sp2 hybridized atom. So think about how many electron domains you have. Electron domains. And so I have 3 domains, and they want to get as far apart as possible. So I form 3 hybrids. Well, that means I need 3 atomic orbitals. You always start with an S. So I have an S and 2 P's. So sp2. Okay. If I have 4 domains, like the one on the left, then I've got an S and 3 P's, so that's a sp3. If CO2, it's got 2 electron domains, I only need 2 hybrid orbitals. I have an S and a P, so it's sp hybrid. So review that. It helps you look up, okay, the angles between those two. sp is 180, sp2 is 120, and sp3 is 109.5. So those things should be in your head. So what is symmetry? We've used this term a whole bunch, and I'm going to jump quickly through this because we're going to learn by doing. So in this case, symmetry is defined by the number and types of symmetry operations that leave the object unchanged. So if this is water, my head and the 2 hydrogens, and I rotate it 180 degrees, and you closed your eyes, and then you open them again, you couldn't tell I did anything. Like the water, you had the same shape. Water here, I rotate it, you look, open your eyes, you still have the 2 hydrogens here, you still have the oxygen. You wouldn't know that anything happened. And so that's what we mean by leaving the molecule unchanged. If this was water and I rotated it this way and you open your eyes, you'd see the hydrogens up here and they used to be down there. You would say, no, something's happened to the molecule, it's not unchanged. So that means that water does not have a rotational axis this way because that doesn't leave the molecule unchanged. But it does have a rotation axis this way because you can rotate it and it leaves the molecule unchanged. So that's what we're looking for. Things you do to the molecule that leave it unchanged. And here are the only symmetry elements that we've identified, okay? There's 5 of them, but one of them is just do nothing. It's the identity. It's like multiplying by 1. We have the CN axis. If we rotate this 360 divided by 2, that's a C2 axis, which is 180 degrees. If we divide it by 1/3, then that's a C3 axis. So how many how many times you divide the circle. So 1/4 of a turn would be C4. 1/8 of a turn would be a C8. Then we have a reflection plane. That was the water that I showed at the very beginning, the surface of the water. An inversion center, you probably learn by doing. Every atom in the molecule inverts through the center and goes to the other side. And if there's an atom on the other side, think of benzene. The carbon hydrogen bonds in benzene, the hydrogen can go through and meet its partner on the other side. Okay. And then the SN is a rotation and a reflection. So let's look at these on Symmetry. I'm just jumping ahead because we're going to learn by doing. So this page, Symmetry, you need to go there, bookmark it, practice on this. This will teach you all about symmetry. Okay, so I'm going to go here. Yes. Yeah, good. I'm just making sure that the video is capturing this. Okay, so we have the Symmetry website. I'm gonna have to run it sideways because I can't see my mouse. And so here's our symmetry elements, and we're going to play around with these. So let's go to the reflection one. So here's ammonia, and over here we can turn on all the different reflection planes in ammonia. See, each one of those is a reflection plane. The cool thing about this, I'm going to turn them all off. I'm just going to pick this one, is you can animate it. See how it reflects into itself? That's beautiful. Okay, let's do this one. See how it reflects? We can turn that one off, turn that one on. Let's do benzene. This was great. Okay, it has sigma D reflections, dihedral reflections. They all bisect the dihedral angle. So this is the angles between these two bonds would be a dihedral angle. And so the sigma D's break those dihedral angles. And now let's reflect the whole molecule. Let's close that off and just do one of them. Can you predict what's going to happen? The whole thing's going to reflect. See, it kind of looks like it's rotating, but it's not rotating. Let me rotate it and move it like this. You can see it's just reflecting. Okay, so that's the reflection plane. Pretty easy to understand. Let's go to inversion, and let's do benzene. Okay, it has, by definition, you can only have one inversion point, and it's right there in the middle. It does not have to be on an atom. It's the center of mass of the molecule. Can you predict what's going to happen? Watch all of the hydrogens and the carbons too. They go through that point to the other side. Okay, this one's trippy. Okay, let's look at that thing. Come on. Come on. Why are you going to mix up on? That's beautiful, isn't it? Okay. This makes such a great video. Try it again. Isn't that crazy? Yeah, so I've lost the Wi-Fi. That's what's happening. Thank you. We did see the inversion though. And you have the website, Symmetry. So you can go, if your lab's today, maybe, while you're eating lunch, play around on it. But you'll get some chance to play with it. Or we'll see you next time.